All right, so today we're going to be reviewing image weighting and contrast. All right, so here we have our two axes where we have the longitudinal vector or axis, m sub z, and then we have our transverse axis, which is on the x-plane here, m sub xy. Our net magnetic vector aligned with b sub 0, which was our static magnetic field. And when we hit it with an RF pulse that was at the same frequency as our net magnetic vector that rotated around b sub 0, it gained energy and it was able to flip into our transverse plane. So this vector is now in our transverse plane. All these spins are in phase with each other and they're rotating around this axis 360 degrees. This is where we have our receiving coil so that we can collect this signal, which is ultimately our net magnetic vector. That's our signal. So we're collecting it because this is a rotating magnetic field around a stationary coil, and due to Faraday's law of induction, that will induce a current within that coil. Okay? But we don't want to sample right after we flip that vector into that transverse plane. And why do you think we don't want to sample it at that moment, where all those vectors are right there in that transverse plane at the same length? What do you think?
No contrast between fat and water.
There'll be no contrast between fat and water and all those other vectors, right? We'll have great signal because these vectors are very large, but there'll be no contrast between those tissues. So the image would almost appear as just a bright white image where you could not differentiate all the different tissues. So good. We want to turn this RF pulse off and allow those tissues to relax back up that longitudinal axis. And what's happening when we turn that RF pulse off is the high energy spins, because we gave energy with this B1, start to lose energy. So they go back to that low energy state, which is where they're happy. And so that net magnetic vector realigns with B sub 0. And this is the course it takes. It loses transverse magnetization and it realigns along the vertical axis, which is our longitudinal plane. And it goes up in this regard because, remember, this vector still precesses around B sub 0. So in terms of T2 decay, our spins are no longer in phase with each other. They start to dephase rapidly, and they're termed incoherent or out of phase. And that signal decay is also referred to as our free induction decay. And we can see how we get that image here where our amplitude goes down very rapidly, and it comes from this, where the transverse signal is decaying very rapidly. Okay? So we can think of this as two separate processes that are happening at the same time. Okay? So our T1 recovery is also termed spin lattice because we're getting off energy to our surrounding environment or our neighboring spin. Surrounding environment. So other tissues. So when we diagram this curve, just take note at how we label these axes. So for our vertical axis, it's m sub z, so for our longitudinal plane. And then our x-axis is going to be same for both, and that's just time. And what is our unit for time? It's milliseconds, because these things are going to be happening very fast. Okay, so when we think of recovery, we think of things kind of coming back. So we didn't have any longitudinal signal when the RF pulse was applied, and it was all in this transverse plane. But the moment we turn it off, that signal or that vector starts to regrow along the longitudinal plane. And we consider tissues fully recovered once they've hit 63%. Because we don't want to wait for all the tissues to fully recover, because once again, we're not going to get any contrast between those tissues if we allow all those tissues to fully recover, and they'll be the same length in terms of vector size. So another process that's happening at the same time is our T2 decay, which is also referred to as spins, because the hydrogen proton is giving off energy to its neighboring spin. So here our y-axis is the transverse plane, so magnetization xy. And at this moment, we had applied that RF pulse and our vectors in that transverse plane. So we start off at 100%. And since it's called T2 decay, our signal and our vector length and size decays rapidly. So we consider a tissue fully decayed when it only has 37% remaining. Or you could also refer to it as it has lost 63% of its value. Okay? So that's how we get these two numbers. And it's important that you remember these two percentages in terms of fully decayed, fully recovered. All right. So in the book and on the registry, they like to talk about two specific tissues, fat and water, because they're on the complete opposite ends of the spectrums, just due to their molecular makeup. So this is what water looks like, H2O. And it's polarized because the oxygen atom is pulling those electrons away from hydrogen because it wants to have that full, complete outer orbital shell of electrons. So when it does that, it makes the oxygen side more negative because it has more electrons in its orbiting shell than it normally does. And then the hydrogen side of H2O is more positive. And when you polarize something, it becomes like almost like a little bar magnet, because you have a dipole effect where one side's negative, one side's positive. And when you get a dipole effect, that strong magnet, B sub 0, is going to affect it more. So we can say the hydrogen in water is more available to the effects of B sub 0. And this results in a higher Larmor frequency. So water processes around B sub 0 slightly higher than fat. And it has a faster tumbling rate. So since it processes slightly higher than fat, it actually doesn't match up with our Larmor frequency as well. So with all those things combined, it does not give off energy to the lattice and to its neighboring spins as easily. Okay? And this is really dealing with the lattice. Water is also a liquid, right? So water, if you put it in a beaker, those little water molecules are free-flowing. They're not as closely packed together. So this is where you get the T2 decay, because you're not giving off energy to the neighboring spins as quickly. Okay. Fat, on the other hand, the hydrogen here, they're sharing the electrons with whatever they're attached with, carbon, oxygen. So it's a covalent bond versus an ionic bond. And so they're not as available to the effects of B sub 0. They process a little bit slower than water. So that's why, in terms of giving off energy to the lattice, the Larmor frequency matches up a little bit better, so it's going to give off energy to its surrounding tissue a lot quicker. And in terms of T2 decay, this is a very big molecule, and if you put fat in the beaker, it just kind of sits there. It's not free-flowing, so it's going to give off energy to the neighboring spins a lot easier as well. Okay? So all in all, water, we can say, has an inefficient energy exchange with its surrounding environment, lattice, and neighboring spins. So it has a slow recovery and a slow decay. But on the other hand, fat has a very efficient energy exchange, so it's going to have a rapid recovery and a rapid decay. So when we draw those two curves on our T1 and our T2 decay, this is what we get. So let's talk about water first. So water has a slow recovery. So you can see here it recovers, but it recovers very slow, back up to 100%. Compared to fat recovers very quickly. So if we had that 63%, which we remember considered when tissues were fully recovered, we draw that line over to both curves, and we get the T1 relaxation times for fat and water. And which one has a quicker time? It's fat, because you can see at 63, it took less time than water. So we could say this is a TE1, and this is, I'm sorry, not TE, TR1, sorry. We're governed by TR on our T1 recovery. So this is TR1, repetition time 1, and that's associated with fat, and this is our repetition time 2. That's associated with water. But if we had to break this down in terms of milliseconds, you could see that the time for water would be longer than the time for fat. And we could do the same for our T2 decay curve. So water, once again, has a slow decay. So we can see that curve here, slowly decaying. But then fat has a rapid decay. So it loses signal very quickly. So then at 37%, we draw our line over, you can see that we have T2 decay times for fat and water, and it's governed by time constant TE, so we have two separate TEs. TE1, which would be for fat, and TE2, which would be for water. Okay. And once again, you can see that water would have a longer TE than fat. Yeah, for what?
So the first point up there about the molecular tumbling frequency and the normal frequency.
Yeah.
Exactly is the molecular tumbling rate? Is it referring to the entire molecule tumbling or the spins precessing?
It's the entire molecule tumbling. Yeah.
And that
Because that's a little different than the Larmor frequency matching, because the Larmor frequency matching is talking about the spins precessing. And they don't match up as well. These hydrogen spins don't match up as well as the Larmor frequency. Okay. Of just a normal hydrogen proton. Okay. So they don't match in terms for water, and water tumbles at a quicker rate. And both of these things combined means that water and the hydrogen within water doesn't give off energy as efficiently to its surrounding lattice. Okay? So these two are really dealing with T1, and then this one being a further spaced molecule, that's really dealing with T2, because you can see here that the neighboring spins, and this is dealing with its lattice. Okay? And this one kind of also goes with number 3, because it has a higher inherent energy because it maintains that energy and doesn't give off energy to its lattice as well. Okay? But tumbling, that's that whole molecule and how it just kind of end over end. That's what tumbling means. Larmor frequency, it's just talking about this one particular atom and how quickly it precesses around B sub 0. Okay? Did that help any?
Yeah, it does.
Okay.
It does. Thank you.
The main thing you should take away, though, is kind of this right here. Okay. Due to these factors, this is what's really happening. It's really just an inefficient energy exchange, and when that happens, it has a slower recovery and a slower decay. Okay? But this is kind of really the reasoning behind it. All right. So let's go on to this next document. So we have this one right here. And it's similar. But there's other things that we talked about in this unit. And it really was intrinsic versus extrinsic parameters. So intrinsic parameters are things that we cannot manipulate. So they're inherent to the tissues. So each tissue has a T1 recovery time and a T2 decay time that we can't change. We can manipulate our TR and TE to kind of highlight the differences in tissues, but we ultimately can't change those recovery and decay times. We also can't change how much spin density or proton density we have in tissues. So the number of hydrogen protons within a unit of volume, which is a voxel. That's all that's saying, what proton density is. Flow is something inherent, and that's dealing with CSF and vascular flow. And then our apparent diffusion coefficient, ADC, water molecules, or just water diffuses through cells at specific rates. But we do have extrinsic parameters on our MR console that we can change to give our desired contrast. And those things are repetition time, echo time, inversion time, flip angle, and I just put it in here as a reminder, flip angle is determined by RF amplitude or strength and how long it's applied for, duration. Turbo factor, echo train length, and B value, which is associated with diffusion. This part was on the previous document, so I'm not going to go over this again. But what we do have here is our actual values. So I actually included in a little chart here our T1 recovery time and T2 decay times of fat and water. And this is, remember, at 1 Tesla, because it's field strength dependent, at 1 Tesla. So fat has a very short recovery time and a short decay time, 200, 100. Water, on the other hand, has a long recovery time, 2,500, and a long decay time, 2,500. All right. So then we got into, that described contrast. But then the second half of our unit really talked about weighting. And that's, remember, how we manipulate those extrinsic parameters to get the desired contrast that we want on our image. Because contrast is no different than what we describe in X-ray, where we have white and black on our image and different shades of gray. That's contrast. But image weighting is how we downplay or highlight T1 and T2 to get our desired image contrast. So we only really talked about 3 different types of weightings in this unit. Proton density weighting, T1 weighting, and T2 weighting. So let's describe that in a little bit further detail. So when we just want proton density weighting, and what that means is all we care about is seeing how many hydrogen spins are within a voxel of tissue. So then we have to downplay or diminish the effects of T1 and T2. So how do we do that? Well, for our T1 recovery curve, we allow all those tissues to fully recover so they're at 100%. So there's no contrast between those tissues. So we select a long TR. So then how do we diminish T2? We don't let those tissues decay for very long before we sample those echoes. So we select a short echo time where the tissues don't have much contrast difference. Okay? So by selecting a long TR and a short TE, that will give us our desired proton density contrast. So this is why it's a proton density weighted image. So I gave you the ranges here. So a proton density weighted image typically has a TR of between 2,000 and 7,000 milliseconds. And that's considered long TR. It also has a short TE echo time in the range of 10 to 25 milliseconds. That's a short TE. Right? Moving on to T1 weighted. And here we want to highlight T1 contrast, but we want to downplay the effects of T2. So just look at how in proton density we are downplaying both. But here with T1 we want to highlight our T1 contrast, but with our T2 it's no different. So you could basically just copy and paste this down here, and that's kind of what I did. Because we're downplaying T1, we don't let those tissues decay so that there's no contrast between those tissues, so we select a short TE. But since we're trying to highlight T1 contrast, we don't allow those tissues to fully recover up to 100%. We select a short TR so that you can see here how the two tissues have different signal amplitudes. So our ranges for T1 weighting is short. Short TR, 300 to 700, and then our TE is 10 to 25. And then our T2 weighted, we are trying to highlight T2 contrast and diminish T1. So how we diminish it, we allow those tissues to fully recover. So we select a long TR, and then we select a longer TE to allow those tissues to start to decay. They get some contrast between them, and then we sample their echo. And you can see here by selecting a long TE, it will maximize or highlight T2 contrast. So then here is the range for a T2 weighted image. A long TR, 2,000 to 7,000 milliseconds, and a long TE, greater than 60 milliseconds. So most places, most clinical sites will have these ranges for their particular scanner, maybe just on a little sticky note at the bottom of the screen of their console. Just kind of either remind the techs working there or students that happen to rotate through. Because every machine is going to be slightly different. So any questions about highlighting and diminishing? So for proton density, what do we want to diminish? Both. For T1 weight, what do we want to diminish? And then T2 weight, what do we want to diminish?
T1.
Good. All right. So with that being said, let's take a look at our images and kind of draw out our curves with our images. All right, so I'm going to draw my T2 decay curve to correspond with this T2 weighted image. So you tell me how to label this. What is this y-axis here? Okay, and so x, y, all right. And then what is our x-axis? Time. And that's in milliseconds. All right. And then let's label or title this graph, and what are we going to call it? T2 what?
Weighting?
T2 weighting. Well, that's the image we're getting, but what's the curve called? T2 decay, also what?
Spin, spin.
Spin, spin. All right. And let's do our two tissues. So I'm going to do water first. And water recovers slow or fast? Water recovers slow or fast?
Water recovers
Slow.
Oh, but you guys are confused because we're talking about T2 decay. Does water decay fast or slow? Slow. Okay. So thank you. So then I'm just going to kind of draw a linear slope going down to 0.
Slow.
So, but I was mistaken. I said recovered, but we're on T2 decay. Sorry if I confused you. So we're doing the T2 decay. So decays slow. So it's giving off energy to its neighboring spin very inefficiently because it's a free-flowing molecule. So it's not giving off energy to its neighboring spin as easily as fat. And I'm going to do orange because yellow will be hard to see. So fat loses signal almost exponentially very quickly down to 0. Right? So at the top here, it's 100%. And goes all the way down to 0. All right, and then what's the percentage I should draw or at least mark on a T2 decay curve? 37. So I'll put it about right here, 1/3 down. All right. So then I'm just going to draw my line over to both. And drop it down to my time axis. All right. So then we have TE1. All right. And what was the TE for fat again, for at a 1 Tesla? What was that number? 100 seconds, did you say? Yeah. 100 milliseconds. And what was the TE time for water? 2,500. Remember, it's at 1 Tesla. Okay, so you can see how we get those two values. All right, so now let's draw our lines over. And water is going to make the most sense for this curve because it is bright white. So you can see that we still have a large amount of signal wherever we sample it at. Okay? So we select a long TE to highlight the difference between these tissues. But no matter where we select it in terms of time, water is always going to have a larger value than fat on this curve. So with that being said, water will appear bright on a T2 weighted image. Right? But this is where it gets a little confusing because our fat, no matter when we sample our echo, fat's going to have less signal than water, and that does hold true, but you would expect it to look completely black, considering it does decay very rapidly. But this reason our signal constantly gets boosted back up, because what actually the curve looks like is it gets boosted back up, and then boosts back up, and then boosts back up, continuously by what we call refocusing pulses, and that's called J-coupling. But fat has lower signal intensity than water, yes, but if it was just a typical spin echo pulse sequence, it would look a lot darker than this. But this is what fat looks like on a T2 weighted image. Okay? Right? So if I had to draw in my two other curves, and let's say white matter versus gray matter, which one do you think decays faster based on this image? White matter or gray matter decays faster?
White matter.
And why?
It's darker.
Because it's darker. Okay, so let's just draw in those curves. And I'm kind of guesstimating at this point, so I'm just going to give it a different color. So I'm going to code white matter as green. So Savannah was right in saying it's since it's darker, and this is white matter, kind of in this area, because it's closer to our ventricles. So I'm going to give it a curve. So in terms of fat, it doesn't decay as rapidly, but once again, remember the 180 pulses. That's maybe something like that. But then our gray matter, which is closer to the edges out here, let's give it purple. Maybe something like that. So I just wanted to highlight that you can have these curves for every tissue. We talk about fat and water all the time, but remember, every tissue has a specific T2 decay time. And that time is when it crosses this 37% threshold. Right? So always go to the fluid when trying to identify if it's T1, T2, or proton density. If the fluid is bright, it's a T2 weighted image. The fat is darker, but also now we know that white matter decays faster than gray matter, so it's going to look darker than gray matter. So that's another way that you can identify a T2 weighted image. So now let's go to a T1 weighted image and draw our curves. All right. How do I label my y-axis? What is that now?
M sub z.
M sub z, for our longitudinal. And then our x-axis, any different? Time, and it's in milliseconds. And then how do we title our graph?
T1 recovery.
Okay. Or spin. Right. So I'm going to do, we consider tissues fully recovered at 63%. 0 and 100. So once we turn off our RF pulse, water recovers slowly because the alarm are frequency matching, it tumbles faster, so it's not as available to the, or it's more available to the effects of B sub 0, so it processes also a little bit faster. So in terms of giving off energy to its lattice, it's not as very efficient. So it recovers very slowly. But fat is just the opposite. Fat recovers very rapidly. Okay. You draw over get our TR times for these tissues. So this would be considered TR1 and TR2. And those numbers were very similar. TR for fat was what? 100, 200. What did I have on that chart? 200. And then water was no different. It was 2,500, right? Okay. All right. So no matter where you select your TR, fat is always going to have a larger signal intensity than water in terms of T1 contrast. So with that being said, we can see that fat, which is just our subcutaneous tissue right here, is very bright on a T1 weighted image, where water, which is in our ventricles, is very dark. Okay? And then if I had to do white and gray matter, our white matter, once again closer to the ventricles, and I think I did green for this, right in this general area. And we said white matter decayed very rapidly, but it will also recover very quickly. That's why it's brighter on a T1. So if I had to draw in my curve for white matter, it would look something kind of like this. Then I use purple for gray matter. So here's our gray matter kind of on the edges out here. Gray matter recovers a little bit slower than white matter. So gray matter has that kind of curve to it. Right? So I'm giving you more ways to identify if it's T1 versus T2. Everybody got this strong? I don't want to erase it quick. All right, moving on to just proton density. And I don't really have to draw my curves with proton density because we're diminishing T1 and T2 contrast. So it's all just based off of how many hydrogen spins we have within a specific voxel. So these are pixels, but just imagine they're voxels, three-dimensional. So if I had, let's say, okay, we have two areas in the brain, two different tissues, where one tissue has more hydrogen spins within that area of volume, or voxel. And if I had to say, if you could point to white or gray matter, which box would be associated with white and which one would be associated with gray? What do you think?
More would be gray matter and less would be white matter.
Good. So you're basically saying we're going to point here to the white matter. So since we have less hydrogen spins within this unit of volume, it's going to be darker on our image. And then our gray matter, which is on the periphery here, is going to have more hydrogen spins within that specific tissue, and it appears brighter on our image. Good. So proton density weighted it's really, we don't even have to worry about the curves because we're diminishing them. We're selecting a very long TR so that all these tissues fully recover. They have the same length in terms of vector. And we're selecting a very short TE so that we don't allow those tissues to decay. So we don't see the contrast between those tissues in that regard. So all it's based off, and all this image is created, is just based on how many of those hydrogen spins you have in a unit of volume. And we could say that fat probably has the most spin density compared to other tissues, just because it's the brightest on our proton density. So good. All right. Did anybody have a question about the classwork? So remember, you're supposed to kind of do that on your own. We'll turn this in at the end of the class if you have it done, but if you don't, you can upload it onto Canvas by tonight because you can still have a chance to watch that video that's on Canvas. But did anybody have any questions about any particular? So for these, you're just kind of circling if you want a short or long TR or TE. And then write the ranges in milliseconds. So if you have that, go ahead and turn it in. You can kind of leave it right up here. But there's just one other concept we need to go over before we finish this unit. So go ahead and turn that in and I'll get... All right, so remember, we still have till tonight, by midnight, to turn that on. Okay, so with T1 and T2, in terms of MSK imaging, it's a little hard to find the fluid sometimes because you do have synovial fluid, but it's not always that apparent. So the next tissue that you should go off of, because we can't see white and we can't see gray matter in the brain, is to go off of muscle. And with a T1 weighted image, muscle has a little bit more signal, and it's gray, higher gray intensity, a little lighter than on a T2 weighted image. See how muscle is darker? See that?
Say that again.
Muscle on a T2 is going to appear darker than on a T1. So I'm just saying, if you don't have fluid to go off of, because with MSK, you're not always going to have synovial fluid, fluid in the joint space. So the best way to identify it is to go, the next tissue you should look at is muscle. And if the muscle is very dark, it's a T2. If it's not as dark and is a little bit higher in terms of signal intensity and it looks a little bit more gray, it's a T1. Okay? Just kind of another clue to go off of in terms of identifying for MSK.
T1 is a higher intensity signal.
For muscle. Just for muscle. That's what I'm just talking about one tissue for muscle. A T1 muscle is going to be brighter than T2. On all MR images, there are some structures that are always going to be black. And like, I'm talking about like space black. Like out here where you're not even imaging. What do you think those structures are? On a T1, a T2, proton density, stir, diffusion, all these images, these structures are going to be always black. What do you think they are? Hair. What else? Non-ferrous materials? Or ferrous materials? Non-ferrous materials. Okay. And yeah, so something with no MR signal. Good. I mean, we could talk about all the different devices that we could bring in. Yes. A tissue with no hydrogen spins in it. Yes. But let's talk about like just kind of the makeup of our body. We do have air in our lungs, so it's going to appear dark. Air within the trachea, that's going to appear dark. Cortical bone doesn't have many hydrogen spins within it, so that's why on all MR images, your bones look like they have this kind of highlighter outline to them. See that? Okay. Tendons and ligaments. You can see a little bit of the PCL right here. That's a ligament. And I'll say that with kind of an exception, because if there's some kind of issue with those tendons or ligaments, like if it's ruptured or strained or torn in some ways, then you're going to get signal intensity. Because now edema has kind of gone into that area and there will be signal intensity. Kind of the same with the menisci. Those are typically dark structures on all MR images, but if you have a tear within the meniscus, it's going to appear as a bright signal spot. And then any metal. Metal will cause distortion and signal loss. So if you happen to have like a prosthesis in the patient, it's going to distort the image, cause an artifact, and there will be rapid signal loss, and it'll appear black. So no matter the image weighting, these structures are always going to appear black on MR images. All right, so there's one last little concept we have to learn for this unit, and it's called partial and full saturation. Okay? So it's best shown through diagrams, just like a lot of things in this. But the actual definition is when the net magnetic vector gets pushed beyond this transverse plane, beyond 90 degrees, that is considered partially saturated. So whenever this vector, as you can see with these two vectors right here, they're beyond 90 degrees, they haven't been completely inverted, 180 degrees, but they're between 90 and 180. That's considered partially saturated. A vector is considered fully saturated when it goes past the 90 and then it actually gets completely inverted, 180 degrees. That's considered fully saturated. And what ultimately does is it diminishes signal. Both of these ultimately just diminish signal because they're not on that transverse plane. And what we're talking about is when we're delivering repeated RF pulses. So we've talked about that excitation pulse, which is usually the first RF pulse that flips that vector into the transverse plane. But remember, we're not allowing these tissues to fully decay and fully recover because we want contrast, right? So there's always sometimes going to be a component of transverse magnetization still left when we hit it with the second RF pulse, okay? And when we hit it with another RF pulse, depending on whatever flip angle that is, it's going to flip the vectors that are still in that transverse plane another bit. And it usually pushes it past that 90-degree threshold. So up to this point, I don't want to over-confuse you guys. I just don't want to confuse you guys on these concepts. But the main thing you need to know is what partial saturation is versus fully saturated. Partial is past 90 degrees, and fully saturated is what we call almost inverted. That vector is gone 180 degrees, and it'll be pointing down. But this is a concept when we're talking about repeated RF pulses. Repeated RF pulses, where we're hitting those tissues and those vectors with another radio frequency pulse. And ultimately what it does to our image is diminishes signal. So it's not a good thing. But we'll get to how that is incorporated into our pulse sequences here in a little bit. But this is all you need to know about saturation thus far. So I don't want to overcomplicate it. So I'll leave it at that. Any questions about anything? Because your quiz is do Tuesday night at midnight. I believe it's around 50 questions. Quiz test, yeah. Midnight on Tuesday before we start our next year. But we're going into the lab on Wednesday. All right.